So if you have, remember, these are the type of problems. You have, the very least, you have two parameters. This is unknown, this is known. Look at the counter problem. The same two parameters unknown. See, two unknowns, so you need two estimators. We like them to be unbiased, right? Then we can, once we have an estimator, we can compute their variances, right? That much is good. So this you need to do. Same thing here, there is only one unknown. You have an estimator. We want it to be unbiased. You may not be lucky. You may never be able to find an unbiased estimator. But once we find an unbiased estimator, what the Cramer Rao bound say, and you can of course compute its variance. Then if you have an unbiased estimator, this is the condition, right? This is the thing we have learned. The variance is going to be greater than or equal to the Cramer Rao bound. Okay. Same thing here. This variance will be. So the question is, how do you compute the Cramer Rao bound? This is where we went through this. And even though I used the same notation, by now you know that this quantity and this quantity are not the same, right? So you can start putting wiggles and so on. I'm going to show you for two parameter case that this is worse than this. Okay. So what that means is what? What that means is, if you bring in more, philosophically it's fine. If you bring in more uncertainties, even the bound on your variance gets weaker and weaker, right? So again, just saying that find me the Cramer Rao bound doesn't mean anything. It has to be done in the context. In this context, it will be one Cramer Rao bound. So of course, as I said, you can you can make all sorts of. So if you plot these two, it will be like this. You see. So I'm going to represent this as say in black, and this is in red. Then it will be like this. So this may, the axis itself may be signal to noise ratio or something, right? So my point is both are sigma squared CR, both are for the same parameter, but the difference is you have more uncertainty. So how did we do this? So very quickly, multi-parameter cases, you have several unknowns, k unknowns, and you also have k estimators, which are, I'm tactically assuming that I have unbiased estimators. Remember, this itself is a big job. That's the whole art of, you can look at the maximum likelihood estimators. They may not be unbiased, but then you do this and that, right? Or you find an estimator, then you use the Rao-Blackwell theorem to find the one with the minimum most variance and so on, right? Then I said, let's arrange all this in order like this. If we created a vector of the, I created an x vector with t1x minus theta 1, t2x minus theta 2, etc. tkx minus, remember x is the whole data vector, minus theta k. Of course, this is not the same data vector, just a notation, right? So expected value of this is 0 because expected value of this is theta 1 minus theta 1, right? So expected value of big X is 0. Then I created a y vector which is taking the derivative of the log likelihood function of all the data with respect to theta 1, theta 2, etc., right? Generally we do with respect to 1, but now since you have so many parameters, you can do with respect to all of them, right? I'm not going to do the whole derivation, I'll just bring this up for you. So this is All right, so, and expected value of y, anybody? What is the expected value of y? 0, because look here, expected value of y is integral, right? Take any one of them, integral this multiplied by the density function. This is what? So that is df by d theta k 1 over f. Then because it is expected value is what? Integral multiplied by f cancels. Then if the regularity condition is true, the d by d theta k go outside. So you get integral f. This is 1, so so that's going to be 0. This is true for all of them, right? And expected value of, how about expected value of x, y? Remember, that's x, y transpose rather. So x is like this, y transpose is like this, right? X is like this, y transpose will be, so this will be n by 1, 1 by n, so it will be an n by n matrix. So a typical entry will be here, it will be like xi, yj, right? This will be x1, x1. So I did this for you, so this is the expected value of y is also 0. So let's look at, in this matrix, let's look at a typical entry. So that's expected value of xi, yj. Xi is what? Expected value of tix minus theta I, right? This is the ith entry here. And the jth entry, there is theta j log f x theta. Anybody knows the answer? What do you get? We went through this. So you see, expected value means what? Multiply by the density function. So tix minus theta I. So the d log f is what? 1 over f df by d theta j multiplied by f cancels, right? So you have two terms. So the this is tix df by d theta j minus another term integral. Theta is a constant, right? Here you have d by d theta j of f, right? This is theta I. Let me not get sloppy here. So this is j. Okay, I mean, of course, dx, etc. What is the answer to this, anyone? By regularity condition, the derivative goes outside regularity condition 1. Integral of df is 1. Derivative is 0. So he is right. That term is 0. How about here? Regularity condition 2. This goes outside. Then what? Then what do you see? Integral tix fx dx is what? Integral tk fk is, remember, this is integral tk f dx, right? That's theta k. So that's what? So this is d by d theta I of theta j, right? Because the integral will turn out to be integral theta I f. That's going to be theta I, right? Derivative is with respect to theta j. Hello? Derivative is with respect to theta j. What remains is theta I, right? Ti fx dx. So this is theta I. So we get the partial derivative of this. So this is your delta function, right? So what is my point? This matrix will be all ones along the diagonal and 0. So that's an identity matrix. Okay, we went through this last time. All right, so seeing that, now I am going to define a vector z, a bigger vector, as z or y. Okay, I just put it one below the other. I put this below this. and this I'm going to call this thing as a z. Fine. So it's a long vector. Again, expected value of z is 0, right? Because expected value of each component is 0, right? So let me get rid of all this. We'll use this expression. So let me find the covariance matrix for z. This is a standard trick. I just want you to, so that you can use this in, so I'm going to do expected value of z transpose. So any vector multiplied by its transpose is, expected value is positive. Anybody knows? I went through all this last time. Why is this true? Right. Or remember, what is the definition of a matrix being positive definite? We say R is positive definite means if you multiply R with any other vector from the left and right, this should turn out to be a positive number. So let's see whether this is true here. So let me multiply this with a vector, then you have expected value of z. Remember, of course, this vector has to match the size. So if this is m by m, I want this vector has to be m by 1. This will be 1 by m. So that's understood. If this is m by m, this will be m by 1. This will be 1 by m. So the whole thing is a scalar. And it makes sense to talk about a scalar being positive or not. Okay. So same thing. So remember, this is of size k. This is size k. So z is of a vector of size 2k by 1. So I am going to multiply by a z. This z vector is going to be 2k by 1. Because this is 2k by 2k. This is 1 by 2k. Okay, so the whole thing is scalar. And now if you see, let me take, remember this is not random, this is random. So I'm going to take this inside. So I can write this as expected value of z star z multiplied by z star z. Because z is scalar, so whether a transpose or transpose conjugate is the same. Okay. But you see, this is suddenly a scalar. Because this is 2k, 1 by 2k, this is 2k by 1. This is 1 by 2k. Each of this is 2k by 1. So this is 2k by 1. So this is scalar, this is scalar, this is the complex conjugate of each other. So this is of this form, expected value of c squared, where let me call this to be c, then this is c star. But the expected value of any positive random variable is positive. Okay, so that's the argument. But on the other hand, so we know that this is positive definite, but this is xy, and its transpose is x transpose y transpose. So if I write it up, I'll have 4 entries. I have expected value of xx transpose, which is the covariance matrix of x, expected value of xy transpose, expected value of yx transpose, expected value of yy transpose. We just proved that this is identity. That's what, right? 5 minutes back. So I can write this as covariance matrix of your this vector. So let me write it as t rather than x. Anyway, it is too late, but you also denote this as t, because t is the, so that's t is that vector of all the t1, t2, tk. So either you can call t to be, maybe that's good, t to be t1x, t2x. So its covariance matrix is what? The vector minus the means multiplied by its transpose. So that's what this quantity is. And this is identity, this is identity. This I'm going to call J. We know that this is non-negative definite. So J is called Fisher information matrix. Again, we went through this last time. Someone told me I went a little fast. So there is no harm in redoing this one more time. But so J is of course a matrix with, let me call the ijth entry to be, remember, so what is Jij? So Jij is expected value of yi, yj, right? From here, this is the Y matrix, ith row and ith column cross multiplied. So that will be expected value of derivative of the logarithm of fx with respect to theta I multiplied by derivative of the logarithm of fx with respect to theta j. So this of course you need to compute. So for example, jii will be what you are familiar with, expected value of the square of d log f d theta I. So this of course will be positive, but this may not be positive because it's a derivative with respect to. So whole point, so you can see it's all the conceivable derivatives are here. I left these notes here last week and it is still here from last week. No one wants these notes. Oh. So you can see the interdependence, what does one parameter do to the other is going to come through this. And then I showed you last time, I manipulated and showed you that. The question is, what is the relation? How do you simplify this? I showed you that if you multiply by a matrix on the left and the right, then, so the key is we came up with covariance matrix of this T vector is greater than or equal to J inverse, okay? J is this Fisher information matrix, so you need to find its inverse. So remember, J inverse is a matrix like this. Because it is J inverse, we'll write it as J11, J12, etc. So all the diagonal entries are J22. If you want to write this, we will write this as J top bottom 11, J22, etc. JKK, Jij here, J1K, JK1, right? J inverse we will write, this is a standard notation, JKK on the numerator. I asked you to show that, now remember on the left hand side here you have a matrix which will be, first entry will be the variance of the first estimator T1. The second diagonal entry will be variance of T2 or theta 2 hat, right? This will be theta 1 hat. T1 is theta 1 hat, right? Theta 2 hat, etc. Variance of theta k hat. And this will be covariance of theta I and theta j hat. So you have the answer for everything. So you can, of course, now you can compare this number with this number. So we conclude that variance of some theta I hat, which is a function of data, is going to be greater than or equal to Jii. Whereas if there is only one parameter, it will be it will be the Jii from here. So let me do this now. So remember, I showed you last time, if you look at the notes, it's also there in the book, etc. How this comes up. You just have to multiply. You can remember these are matrices, so you can't say this multiplied by this minus. You can see it's but the same idea. Or another way to do is, if you know how to take the inverse of a block, consider this to be, of course this is a block matrix. If you know how to do the inverse, it will follow from there also. Let me see whether I have the formula for the inverse of A, B, C, D. Many ways you can do it. I showed you but unfortunately what is in the book is one step is wrong. I just got sloppy, but also this formula will help you. So I'm going to, don't miss the exam because I don't want to redo another exam, etc. And maybe let me try to finish a little early so that if you have any specific questions with respect to, I don't want to stand here and start solving problems for you, but I can, if you are stuck somewhere, you want to ask me something, we can do that. I mean, this is no big mystery. All you have to do is go home. So what look at, it's an identity. What I'm telling you is that the inverse of this matrix, block matrix, is this. Of course, your immediate question is, why is this true? That's easy for you to verify. Go home and multiply A, B, C, D with this matrix and use this. If you spend about 10 minutes, you will see that the whole thing will turn out to be identity. So you can verify it, right? So once you verify it, you know the result is true. So that much you can do. So let's use it for our special case. This should work out. So we have covariance of a covariance of, what is it, T, I, J inverse. Okay. So this will turn out to be from here. Only thing that's interesting for us is this, the last entry. Look at the last entry. Will turn out to be what is it? J minus C is I, right? Covariance of T, this inverse, right? Right. And you have some stuff here, and F is what? So whatever, you have some stuff here, but you know that this is also non-negative because if, okay. So in particular, if you, another yeah, inverse of this whole thing, right? So this is another way to prove it if you want. So we know that this entry is non-negative. So its inverse is non-negative. So we have J minus covariance of T inverse is non-negative. So J is greater than or equal to covariance of T inverse. Then you take the inverse on both the sides, or you bring it to this side and bring the other one to that side. You get covariance of T is greater than or equal to J inverse. Another way to prove it, okay? But I proved it this last time. So let me try to do a example for you at this point, or at least I'll sketch an example. As I said, this is a useful identity. You should, all you have to do is just multiply the left side and right side, right? Multiply without this, multiply this with this and make sure you get I. That's what I mean by identity. Then you know that this quantity is the identity of the other one. See, if I can show ABCD multiplied by X, Y, Z, W, if this is identity, if I can show, right, then this quantity is the inverse of this. So that same logic. ABCD multiplied by that, you show, is a big identity matrix. So in particular, if I remember, I wrote down those two parameters. So let's just do theta is theta 1, theta 2, right? So you can do three parameters at home. So I have a T1 and T2, right? So expected value of T1 is theta 1, expected value of T2 is theta 2, or both are functions, unbiased estimators, right? So in this case, the J is what? J has 4 entries, right? J11, J12, J21, J22. Explicitly, J11 is what? Expected value of d log f over d theta 1 squared, right? J12 and J21 are the same because notice that this will be expected value of d log f over d theta 1, d log f d theta 2. If you flip these two, you get J21. So they are the same. So I can write it like this. And J22 is expected value of d log f d theta 2 squared. Okay. Now remember, I had two problems. So if theta 1 is unknown and theta 2 is known, then we don't get into this J22 and so on. Then of course you had a T1 of x in this case, and it also happened to be unbiased. And we know that the Cramer Rao bound in this case is, anybody? What is it? What is the Cramer Rao bound in this case? Hello? Look. Anyone? Cramer Rao bound. Look here. I have one parameter. I have an unbiased estimator. So what do you do? Huh? From using this notation, can you tell me what it is? Oh, no. So what is it? It's just this, right? This or the. So 1 over J11, right? Okay. So we know that. Right? Now if you, so that's the left side. Okay. Now here I said theta 1, theta 2 are both unknown. and I come up with estimators T1 and T2. Both are unbiased. And remember, here it's a different issue. You can also find the variance of this T1. Now, it may equal to this, or it may be greater than that. If it is equal, if it is efficient. If it is not equal, it is not efficient. If it is a function of the sufficient statistics, then you know that it's umbu, and so all those things. Okay, so anyway, we can say that this is true. Okay. And so that's done, right? Now here again, let's say we got lucky and we found unbiased estimators for each one of them, right? So I'll write here, right? So according to the this result, you see, you need to find the j, you need to invert it. So I have the j there. So j inverse is what? I have to find j inverse. J inverse is 1 over the determinant, which we can do. So let me write it here. So remember, 2 by 2 matrix, you can do, what is the determinant? J11, J22 minus J12 squared, right? As I said, these two entries will be equal because you can, this is the same as J21, okay? Multiplied by, what are the entries here? This is J22, this is J11, this is? Okay, so that's good. Yeah, it's the same. So you see, this I'm going to write it as J11, J12, J12, J22. Okay, so J11 will be, of course, J22 over J11, J2. So remember, according to the, if two unknowns are there, then the sigma squared C are the bound for the first one is given by J11, right? So that's going to be, if you want, you can write it as 1 over J11, right? You pull out J22 outside, pull this from outside, then you can write this as first of all, you know this quantity is positive, right? We also know that J11, J22 minus J12 squared is positive. Why is that? Anybody? Why is this quantity positive, the determinant? Because that's the property of a positive definite matrix. If the matrix is positive definite, its determinant is a non-negative number. So this is the determinant. Look at here. That means the J12 over this quantity is less than 1. So this is 1 minus epsilon, positive. So 1, look at here. 1 over a small number. This is never negative. Why is that? Look at the argument. This number is smaller than this. Why is that? Look at here. J12. So we have, so this is like an epsilon, this whole thing. Epsilon itself is smaller than 1 in magnitude. Epsilon is positive and smaller than 1. So 1 minus small will be also small. Inverse of that will be larger than 1. So this factor is larger than 1. Look at this. This is the Cramer Rao if there is the second unknown is not there. If there is only one unknown. So that is getting amplified by a number which is larger than 1. So you can say this is the degradation parameter if you want, right? I am saying from here you can see that J1 squared over is less than 1, right? So that you plug it in here. So this is like an epsilon. But epsilon is also positive because this is positive, these numbers are positive. Right? So epsilon is positive and less than 1. So this is like J11, 1 over J11 multiplied by 1 minus epsilon. But this is greater than 1. this whole quantity is greater than 1. I just went through the argument, right? This whole quantity is greater than 1. Why? You're looking at me as if... Remember, hello, look here. Epsilon is greater than 1, but less, I'm sorry, greater than 0, but less than 1. So 1 minus epsilon also is greater than 0, but less than 1. So inversion of that is greater than 1. That's what I mean by here. So remember, I asked you, you obviously have to have some way, this quantity is not, you have to, both are, my point is both are Cramer Rao bounds for the same parameter, but in one case the second parameter is known, the other case the second parameter also unknown. So you can see that, I just showed you that this quantity is larger than this quantity, right? So you can, if another way to see the degradation is, right? Isn't this true? The degradation in bound for theta 1 due to, yeah, you can leave it. Thank you. Due to when there is a second unknown, right? We are talking about the same thing, but there is a second unknown is this quantity. So if I substitute that, you get J22 minus J11 J22 minus J12 squared over 1 over J11. So if you bring it under the same denominator, you have J11 J22 minus J12 squared. So you have J22 J11 minus so this whole thing turns out to be J12 squared my point is it is positive. So so you can see that's so this is the penalty we pay because of the additional parameter. Okay. Now of course you can take your specific problem and plug it in, and right. This is the degradation in bound in the Cramer Rao bound due to the second unknown. This is the bound in presence of the second unknown. This is the bound for the same parameter without the second when the second one is known. So the difference will give you the degradation. So a classic problem is in radar. You have a signal is coming, you estimate its direction. But now, of course, you have one more signal is coming. Or in communication, you have two parameters to be estimated. So now you can say, of course, this makes sense because everything being equal, if you have more job to do, things get worse. So at least this is. Now, there are some interesting cases. It is possible, in some case situations, it's possible that these entries are 0. J12 could be 0, in which case, so let me just talk about that for a minute. So if J is diagonal, there is no degradation because look here, J is like this. So J diagonal means, remember, somewhere we wrote these cross derivative terms are 0. That's what it means. If J is diagonal, then it is like this. You only have diagonal terms. So J inverse is what? Anybody? What is inverse of a diagonal matrix? What? Yeah, inverse each entry. So this is 1 over J11 or 1 over J22, etc. rest is 0. You see, so this is so that you can write as J11, etc. So J11 is the same as 1 over J or JKK. JII is the same as J1 over JII, right? So no degradation. So if you can prove that, so the only case where a second parameter won't affect the first parameter is, look here, everything depends on the Fisher information matrix. If you can show that the Fisher information matrix is diagonal, then the other parameters do not affect your ability to estimate the first parameter. So now you can try to see the degradation due to 3 parameters. So J will be 3 by 3, right? So you have to invert it, and more work is involved. So
is there a special situation? Is there something special about the theta 1 and theta 2 in this case, where you get a diagonal matrix, or that could happen to anything?
yeah, it could happen. So let me show you an example. In fact, right. In fact, this is the discussion on this that homework I gave you. So you can try to do that. I'll just give you a hint that that problem is also completely solved somewhere. So you, at the very least, you have to go through the notes and books, etc. Find out where it is. The problem I gave you is a standard classic problem. But first, try to do it yourself. Then the solution is there in the book. So this is the problem. Huh? What is independent? Remember, hold on. What is independent? Tell me. Remember what what is independent?
Theta is independent.
Theta what?
Theta.
What do you mean by theta? Theta is, speak properly. Theta is unknowns, right? So the theta is unknown. Yeah, I mean, you are trying to say something. Say it. What did you mean? The estimators are independent, or?
I mean, if they are independent, this one will be 2, 0.
All right, this is what he is saying. It doesn't have to be independent, right? 2 vectors for, this is not independence condition, right? This means they are uncorrelated, right? What he is saying is the following. If Jij, which is, I guess this is what you are saying. Of course, this was my, J will be diagonal if only all these entries are 0, right? I agree with you, this is a random variable, okay, some random variable, because when you're done, it will be a function of data. This is another random variable. So all this, we know each of these random variables are 0 mean, right? Why? Because we showed a little earlier. So all this means is that these random variables are uncorrelated. They may be independent, I don't know, but we can only say they are uncorrelated, not independent, right? Unless they are Gaussian and so on, right? So that's one and the same thing, but you need all the, but J could turn out to be like this. J may be like this. See, here it is J11, J22, etc. And here it is some JK, K. What I'm trying to say is that a piece of it may be blocked diagonally, diagonal. Other portion may be filled up. You can have all sorts of situations, right? So that means among some of the Jijs this is true, but some of them that is not true. Anything can happen. Okay. So it all depends on your problem. I mean, this comes up. And remember, in almost, even if you take this problem, there are I told you this is the classic problem. How many unknowns are here? Anybody? 2. I see 2 unknowns. That you are really useful. P is of course the power, right? So you would like to know what power is being transmitted. And this, of course, is the carrier frequency. So actually, this may be what you are transmitting. What happens is that this may be what you are transmitting. By the time, so you transmit this, by the time you receive, this happens. You somehow a random phase gets added on the way. So you have this. So this is a random phase. Otherwise, you see, you are not transmitting anything random. You are actually transmitting, look at here, perfectly non-random, right? Just a pure sinusoid. But by the time it comes to you, it may be this, or we have to assume this way. There is also some white noise. Right? As I was saying, this we will assume that it is a random variable where the phase is uniform between 0 and theta. And so the problem is, you see, this immediately 2-parameter makes sense. You want somehow an estimator to compute this quantity, P, and you want an estimator to compute omega naught. Let us say you have, you can assume that you have, so you have x of t, and whatever, you sample t equal to it, so then you have I equal to 1 through n data. This is the data that's available. So you can go home and look at this. This is a classic problem, well studied, 2 unknowns. And you need to estimate the, now if you want to take the attitude that, look, I get something, I also want to estimate this, then you can treat this as an unknown, and then it becomes a 3 unknown problem, as you said earlier, right? So whatever we discussed here, so if you feel that is too hard, make the, what is crucial, if you have to estimate one, would you rather estimate this or this? Anybody? A sinusoid is coming at you, what is the most crucial one?
The power. Because you know it's going to be the same frequency.
No, you don't know the frequency.
Oh, okay. So
it could be, I mean, you may be right, or I was going to say frequency, especially if this is used in to ping something and what is coming back. On the other hand, if it is if it is used as a BPSK communication signal, then this is important, because either you are transmitting plus this or minus this, right? So anyway, you can first try to estimate one, then you have one Cramer Rao bound, otherwise you have to do a J which is 2 by 2, etc. All right, so let me show you a case where J will be diagonal, which will be that example I gave you, at least the part B. So look at this classic problem. Part of it is done, it's done in the notes, but part you will have to do it. Remember, I can generate 3 problems here. First is mu unknown, sigma squared known, right? So this we did in class. Other one is mu known, sigma squared known. So remember, you know how this goes. There are, in this case, the sufficient statistics is what? Anybody? X bar, right? Sigma xi. Right? I don't have to start deriving everything. Or you can call it x bar also, right? You divide by a constant. And we know that mu hat equal to x bar is in fact the efficient and the best estimator, right? Hello? And this is in fact a Gaussian with the mean mu and sigma squared over n. And the Cramer Rao bound in this case is also sigma squared over n, right? And if this case the sufficient statistics is sigma xi squared, right? Mu is known, remember. So you can also write the sufficient statistics as this also, because from this if you subtract a constant, that's not going to change. Remember, this is second is the case where mu is known. Sigma, I'm sorry, yeah, sigma squared is unknown, right? And if I call theta to be sigma squared, then theta hat, as you know, is in fact, L2 over n, right? We went through all this, right? So this is the unbiased estimator because expected value of each of this is sigma squared, n sigma squared over n. So this will be unbiased estimator, and I don't remember the Cramer Rao bound. Anybody? So sigma its variance will be, so expected value of theta hat will be sigma squared, right? And variance of theta hat is how much? Remember, each of this is, if you divide by sigma, it's chi-squared with 1 degree of freedom. So variance of if I define this to be yi, this is chi-squared with 1 degree of freedom. So if I add this up, that's chi-squared with n degree of freedom, if I call this y. Chi-squared with n, I think expected value of y is n, and variance of y is what? Can somebody check it up? I think it is 2n, is it? Okay. Then you see, this you can do this, if I divide and multiply by sigma squared, I can write, so there is a sigma squared here, right? So this quantity is chi-squared with n degrees of freedom. So its variance is 2n. So variance multiplied by a constant is, constant should be squared. So the variance of this, that whole thing will turn out to be 2 sigma 4, right? Because 2n from here, sigma 4 from here. But then I also, the constant is actually this over n. So sigma 4 over n squared. Because of the summation, so 2n sigma 4 over n squared, n cancels. So the variance of this whole thing will come out to be 2 sigma 4 over n. Okay, this we have done in the class. But here comes the problem. The next problem is the homework. One homework. So you have two unknowns. Theta 1 is mu and theta 2 equal to sigma squared. So I'll show you the, so we need to now do two things you need to do. You need to find out, so theta 1 hat, I will say x bar will still work because expected value of theta 1 hat, remember I am dealing with this problem, C only, is mu, so that's good. And this is mean, so that's good. Now, you have to do some work, but I'm going to so this is in fact an unbiased estimator for theta. So let me define theta 2 hat to be 1 over n minus 1. So let me show you this is this will do the job. Okay. So expected value of theta 2 hat is 1 over n minus 1 expected value of summation I equal to 1 through n expected value of xi minus theta minus x bar minus theta. So let me put it this way. I added and subtracted theta. Okay. This need to be squared. Okay. So you see theta goes away, right? So if I expand it, there will be 3 terms. The first term is summation I equal to 1 through n, expected value of xi minus theta, the whole squared, right? First squared. Then minus 2, summation is on all of them, right? So minus 2 expected value of xi minus theta multiplied by x bar minus theta, right? So let me bring the summation here also. So summation is here. Minus or plus rather, right? Plus the last term squared. So multiplied by summation. So that's n xi minus x bar minus theta the whole squared, right? There is a bracket here. Let me simplify this. Look at here. This expected summation is on I equal to 1 through n. On this, so that will give you sigma xi minus summation on this. There is no summation here. So this is like a constant with respect to the summation. Summation, when it acts here, you get n. So you see that this whole thing can be written as, let me pull out n outside. So can't I write like this? So I have 1 over n sigma xi minus theta, right? Because n cancel sigma xi n theta, right? So, but this is x bar minus theta. So I have x bar minus theta here. X bar minus theta squared. So it's a standard trick, right? So I have minus 2n x bar minus theta squared plus n x bar minus theta squared. So the whole thing will give me 1 over n minus 1. And what is the answer to this? Anybody? This, of course, you should be able to answer. Each of this is the variance, sigma squared, right? So this is, you get n sigma squared minus see here 2n xi, so n x bar minus theta the whole squared expected value, right? X bar minus theta squared, as I just told you, this is x bar. This is x bar, right? So x bar minus theta multiplied by x bar minus theta squared, multiplied by minus 2n. Minus 2n and plus n will give me minus n. What is the value of this? Anybody? Okay, but theta is theta 1. Any theta is fine. Let me put theta 1. Okay. Again, it's a regular trick. But theta 1 is mu. So I'm going to replace minus. X bar minus mu the whole squared is what? X bar minus mu the whole squared expected value is? This is wrong, first of all. X bar is normal, but variance is sigma squared over n, right? Hello? Everybody is dreaming? So what is the value of this? X bar minus mu the whole squared. Sigma squared over n, okay? N cancels. So what do you get? Sigma squared, right? So n minus 1 over n minus 1 sigma squared. So after all this, I showed you that that's indeed an unbiased estimator, okay? And this is in fact unview. Because you can see if you expand, I can write this in terms of L1 and L2, the sufficient statistics. Sigma xi squared minus, I think it's, so this is L2. So this estimator is in fact unview. This is unview, this is unview. But the question is, let's also find out the Cramer Rao bound, okay? You have problem? Yeah. Ask me, why are you asking? So look here, is this your issue? You take
I mean, from
here.
x bar minus n and theta 1.
Yeah.
And in the next one, you write it as n x bar minus
Theta 1.
square. Should you write expect?
No, expected value is here, of course. Expected value is here also, right? Yeah, because expected value is going to come on all the three terms. Expected value, expected value, expected value. You're right. But this quantity is, I just showed you, is sigma squared over n, right? Because x bar, theta 1 is mu. X bar is, of course, mean with, normal with mean mu and sigma squared over n, right? So this is sigma squared over n multiplied by n, so this n cancels.
This one is 2 sigma squared.
This one?
Yeah.
2, this is going, look here, you take the expected value inside, before, I'm sorry, you take the summation inside first. And then this is, sigma xi is the same as n x bar. This summation comes here, this is minus n theta 1. N you pull out, then you get x bar minus theta 1. That's the same as this. So that gets squared. So then this is the same as this, so one of them will cancel, you get this one. And this quantity is sigma squared over n. N cancels, you get n minus. So a lot of calculations, okay. But so I'm sort of doing the first part. Now what? So now what remains for you? Again, it is done here, done in the book, so I'm not, and it's a little complicated, but you need to go home and so we have the variance of theta 1 hat. Anybody knows the answer? Variance of theta 1 hat. Yeah, it's right here, the sigma squared over n. And the variance of theta 2 hat, I'm just going to write it down. It takes some time to do it, but it is done in the notes. I think that's the answer. Let me just double check. Right, it's 2 sigma 4 over n minus 1, okay. Now let's find the Cramer Rao bound, okay. So I don't need all of this stuff. Let me just get some space off. So remember that much, so you have all those things going on without, first you need to find 2 unbiased estimators. If you can make sure they are functions of sufficient statistics, then irrespective of all this, you can say this is the best you can do, this is the best you can do also. Both are umbu. That we know that even before you compute the Cramer Rao bound and so on. What you don't know is whether they are efficient or not. In other words, in any case, this is the best you can do. Now let's compute it. So since there is j, you have j11, j12, j12, j22. So j11 is expected value of d log f d theta 1 squared. Okay. So let's compute all the first of all, let me put f of x comma theta is 1 over square root of 2 pi sigma squared e raised, so this to the power n, right? E raised to minus sigma xi minus mu the whole squared over 2 sigma squared. So I'm going to write this as 1 over 2 pi theta 2, right? To the power n by 2 e raised to minus sigma right? In terms of theta 1 is right. Theta 1 is mu, and theta 2 is sigma squared. So next I take the logarithm of f. So that is log 2 pi plus or minus, right? Log theta 2 minus sigma xi minus theta 1. So d log f over d theta 1 is what? So sigma xi minus theta 1 squared over. So this is gone. Derivative of this. Derivative of this with respect to theta 1. So 2 comes here, 2 cancels. Xi minus theta 1, the derivative of this is minus 1, minus cancels. So this is gone. So you end up with the theta 2, I think, right? Huh? No, look at it. Theta 2 is sigma squared, right? That's because we want to take the derivative, that's why we don't want the square, that it will only confuse further. So let's do the d log f with respect to theta 2 now, right? So that is what? So this is a constant. So that's derivative of minus n by 2 theta 2, right? Then this is a constant, so minus sigma xi minus mu the whole squared over 2 theta 2 squared, right? Then this will become plus, right? Okay. So if this is okay, let me take the, let's try to find out J11. So J11 is expected value of d log f d theta 1 squared. So of course I know the answer, but if you want to do it, what is the answer? Anybody? So at this point, since you are not going to take any more derivative, we can write this as sigma squared. This if you want. So you have to square it. So that will be a double summation xi minus mu, xj minus mu, I not equal to j, plus summation I equal to j is xi minus mu the whole squared. The whole thing is squared, so the denominator becomes sigma 4. Sigma 4. Expected value here, expected value here. When I is not equal to j, this is 0. When I equal to j, this is sigma squared, n sigma squared. So you get n sigma squared over sigma 4. You get, so that's J11, okay? And J12 is expected value of, so again, we are not going to take any more derivatives, so I'm going to put sigma 2 as sigma squared. Sigma 2 squared is sigma 4, right? So you have J1, this multiplied by this, right? So you have xi minus mu summation I equal to 1 through n over sigma squared multiplied by minus n over 2 sigma squared plus summation xj I purposely, when I'm going to, remember this summation has no meaning, it's a dummy variable here. And if you are multiplying, you don't want to use the same variable, it will confuse you, so use another variable. That's all you can say, yawning. So you see, this multiplied by this, what do you get? If this multiplied by, this is a constant, when you take the expected value first term, expected value of xi minus mu is what? Hello? So this is minus n over 2 sigma 4 summation expected value of xi minus mu. What is it? Why so much thinking? Xi's are mean mu. So xi minus mu is 0. So the first term is gone. Look at the second term. So this, so you have summation, Yeah. You are not, we are not paying attention. Hello, I copied this wrong. So you have this, right? So you have ij xi minus mu, then I have xj minus mu the whole squared over 2 sigma 6, right? And expectation. Anybody? What is the answer to this? Be careful before you say something. Right? What is the answer? I goes from 1 through n, j goes from 1 through n.
Except for I equal to.
So you have two cases here. You see here, when I is not equal to j, look at me first before, when suppose I is not equal to j, then these random variables and these random variables are independent. Then the expected value is the product of the expected values. So concentrate here. What will be the expected value of this? 0. So when I is not equal to j, this will go to 0, so the whole thing goes to 0. When I equal to j, I becomes equal to j, then this becomes what? Expected value of xi minus mu, the whole cubed. But xi minus mu is a zero mean Gaussian random variable. So what is its third moment? You forget already? X is a zero mean Gaussian random variable with variance sigma squared, what is the expected value of x to the power any odd moment?
0.
Right? 0 seems to be the right answer today. So everything is 0 here, whichever. So you, of course, you have to consider I not equal to j case plus I equal to j case. In both the cases, I just showed you that this quantity goes to 0. You see, so after, otherwise just it's not enough to look here and say it is 0. You have to take all these different cases. So you see, this is a case where j12 is 0. All right, so this happens to be 0. So j12 happens to be 0. And j22, we have to square this. So let me do a little quickly. Let's square this and right, square it. So that's going to be expected value of n squared over 4 sigma 4. Correct me if I make mistakes. Minus n over, remember I have to square this, right? What is j22? You forget the formula. j22 is expected value of the second derivative squared, right? Remember, expected value of d log f d theta 2 squared, right? So I take this quantity and plug it in here. So I'm going to write it in one line. So it's minus n squared, so the square of the first term, n squared over 4 sigma 4. And then, so the whole thing is 0. And then minus 2 cancels, n over 2 sigma 4 is the constant, right?
The 2 cancel.
Well, remember there's 2 2's, right?
Oh, yeah.
2, that's 4 multiplied by, then summation xi minus mu the whole squared. Expected value here, I equal to 1 through n. All right, so that's why I told you to, okay, very good. Plus summation xi minus, this is a mess, the last term, because I equal to 1 through n over 4 sigma 8. All right, this is easy. What is this one? This is sigma squared, right? Xi minus mu expected value is each sigma squared, right? Because there is n of them, so n squared sigma squared cancels, so you get n squared over 2 sigma 4, right? So n squared over 4 sigma 4, n squared over 2 sigma 4. What's the difference? Squared over 4 sigma 4, right? And let's come, so this again, like as before, 1 over 4 sigma 8. Then you have to do this, this is a double summation, right? So this is the same as multiplying this one more time. So I'm going to use a different symbol, right? There was a square, what happened? I forgot, right? All right, so initially it was, each of them are squared, then you have to square the whole thing. So I'm going to multiply by xj minus mu the whole squared, j equal to 1 through n. So here I get again I not equal to j and I equal to j. So I equal to 1 through n xi minus mu, the whole thing to the power 4. Right? When I equal to j, this becomes xi minus mu to the power 4. When I is not equal to j, I get xi minus mu the whole squared multiplied by xj minus mu the whole squared. Everything expected value, okay? So let me write down here because so J22 turns out to be minus n squared over 4 sigma 4 then you see when I is not equal to j, this is independent. So this is expected value of this multiplied by the expected value of the each are sigma 4. I'm sorry, sigma squared. And how many such terms are there? Remember, totally n squared terms. And here there is one n term. So this is n squared minus n. Right? So plus n squared minus n terms with the sigma 4. Right? The whole denominator is 4 sigma 8. Right? And here, this is the fourth moment of zero mean Gaussian random variables. We just, I just gave you the derivation last week, right? Anybody remembers what is the fourth moment of xi's or xi minus mu is zero mean with the variance sigma squared. That is 3 sigma 4, I think. All right, look here what happens. Sigma 4 cancels off. So you get n minus n squared, 4 sigma 4 in the numerator, in the denominator, right? Sigma 4 cancels. So here you have n squared minus n plus 3n because n from here. So you get, bottom line is you get of 2n, n squared cancels. N squared cancels off and 2n over 4 sigma 4, which is n over 2 sigma 4. So let's find out, let's just complete this quickly. So I just found all the terms I need, right? We just found j. J turns out to be, anybody remembers what was? What is J11? Just read it. N over sigma squared, right? And J12 was 0. And this is 0. This was N over 2 sigma 4. So from here, this is of course a positive definite matrix. Look, this is an example where J is diagonal. So J inverse is what? Sigma squared over N. This is 2 sigma 4 over N. So what do you conclude? Look at this, variance of theta 1, same as the Cramer Rao bound, okay? So the first Cramer Rao bound is sigma squared over n, but the second Cramer Rao bound is 2 sigma 4 over n. But look here, the variance, look here. So theta 1, the first estimator is efficient, second one is not efficient. So look here, you have this variance is greater than this. But it is unmu. This is the best you can do in that problem, but it is not an efficient estimator. And moreover, interesting, you see, knowing the other one is not going to degrade this one. This is a special case, whether you know the variance or not, you can always do the best job here. That is, not knowing this is not going to make this estimator any worse, because first of all, the Cramer Rao bound is the same whether this is known or unknown. Okay. So very, now you can try to do the part B where I assume the unknown to be mu squared rather than mu. Even I haven't done it. You do it, I will also do it at home. Then we can compare the results. So, okay.
I'm not sure.
Why?
That variable
Yeah, this is the way. So that quantity is larger than this, right?
Sorry, I think you said before that 2 sigma 4. That
Yeah.
is what they're both.
Oh, yeah. I made a mistake. This is 2 sigma 4, right? It is there in the book. So this part is, what I didn't show you is it takes some time to show that this variance is 2 sigma 4 over n minus 1. So so that's the pain now. In other words, it's not an efficient, it's not an efficient estimator. But it is, at least you can see here, this estimator doesn't affect this estimator because of this. So this is always efficient, whether the sigma squared is known or unknown. Look at here. I think we also showed this, right? If this is known and this is unknown, the estimator is efficient, right? Because in both these cases, both of them are efficient estimators because the variance coincided with the Cramer Rao bound. Okay. All right, now what happens in some cases, especially you try to do something meaningful, the Cramer Rao bound may be difficult to compute. So I'm going to do a last topic. It is not there in the book, called modified Cramer Rao bounds. I think we'll only have time for that. So we can go on like this. I can also try to find you better bounds. Any questions before I proceed? So you realize that from our today's discussion, there is no case where if you are doing so much with one unknown, by bringing in a second unknown, you are not going to do any better than that case, right? You may do worse, but there is no case where the bound will become better. So if you want to summarize, we can say the following. If there is one unknown, you have a Cramer Rao bound, right? If you bring in a second unknown, you don't have to assume that you are going to do worse. It all depends on the j. If the j turns out to be diagonal, then the second unknown is not making your situation worse for the first unknown. Hello? You are still, what is that, something bothering you? All right, then listen to me, what I'm trying to say. You have one unknown, okay? Theta 1 is unknown. And you have two situations. Theta 2 known, theta 2 unknown, okay? Or in both the cases, you can compute the Cramer Rao bound for theta 1, okay? Of course, in this case, it is J1, 1 over J11, right? And in this case, the Cramer Rao bound is J11. You have to compute the, right? So I'm saying it is true. Generally, this bound is, this is true, right? This bound is greater than this. But there are cases where both may be equal. If there are cases when the two bounds are equal, that will be the case when the j is diagonal. So just because you have too many unknowns doesn't mean necessarily that the situation is bad. You may be able to do as good as if there is only one unknown. It all depends on the problem. That's all I'm trying to say. So a second parameter doesn't automatically make the estimator for the first parameter worse than what it would have been had there been only one unknown, right? It's pretty clear. So of course, I gave you all the proof. It all depends on the J, the Fisher information matrix. If it is diagonal, then the additional parameters are not going to affect not going to make the situation any worse in terms of the variance. All right, so this is the Cramer Rao bound for some some parameter. Your variance may be here. Whole point is the variance can only variance can only come and up to. So the variance can be here, but it can go up to here. That's right. That's the whole point of the Cramer Rao bound. Now, if you, is it possible? Remember, the lower bound you want it to be as low as possible, right? So, is it possible to push this down? So that's one direction, one problem we have not addressed. That will be improving the bound. But sometimes what happens is even this is difficult to compute. So we may try to do sloppier bounds. That's what I'm going to do now. They are called, so rather than say sloppy bounds, we'll call them a respectable name, modified Cramer Rao bound. So why are we doing that? Because it may be easy to compute them, as I'm going to show you. So in any realistic problem, as you will see, the Cramer Rao bound may be difficult to compute. So let me just derive that, then we'll do a problem. Okay. I didn't bring this up again, but I gave you the notes. So obviously x depends on theta, but x also sometimes could depend on some other random variable, okay, n. So in any case, as a, let's say this is certainly true, right? The density function of x is this, if you have joint density function of x and y, you integrate out to y, right? So this, of course, I can write it as I can also write, right? This density function is using the conditional density function. You can write it like this. Then what? So remember, what is Cramer Rao bound? Sigma squared CR is I'm going to derive you a different expression. This is certainly what we have studied is d log f of x comma theta d theta squared, right? This is 1 over j11, right? So d log f of right? D log is this, so I can of course write it as d of f of x comma theta, d theta is f of x comma theta, d log f x comma theta, d theta, right? So from here, if this is true for any density function, right? So this is also true, d log of f of x comma theta This is true for any density function. So instead of this density function, I put another density function. So that's good enough. Then what? Let me see whether I remember now. All right, so let me take the derivative of this. Take the d by d theta of this expression. Okay. Derivative on both the sides. So I get d of x comma theta d theta equals integral d of, right? Take the derivative here, same as taking here. I'm going to assume that the regularity condition 1 is true, so it goes inside. I take the derivative of x comma theta given y. This much is true. Now let me use 2 and 3 into this expression. So this is 4. So here you use, see that I use 2, here I use 3. So I get f of x comma theta d log f of x comma theta d theta equals integral d log f of x comma theta given y d theta multiplied by f of x comma theta given y fy dy. Okay. But notice that I'm back to this. Of course, if I want, I can write it as like this. Right? So let me write this as, so remember in the homework 7, part A I did it, part B you do it at home. So let me write this as d log f of x comma theta given y d theta multiplied by square root of f of x comma y comma theta multiplied by square root of f of x comma y comma theta. So this is some function ax, this is bx. You know Schwarz inequality, right? Schwarz inequality says integral ax bx dx, or ax y also here, right? Everything is function. Or we can certainly call it to be ay by dy, okay. Anyway, a square of this is less than or equal to integral a squared x dx, or if you want in terms of y, that's fine. dy and b squared y dy, right? So let me, you can write one more line. I'm going to square this, square of this. Remember, absolute value is not required because it's density function. So squaring this is the same as squaring this, right? It's the same as squaring this. That's where I'm going to use this expression. Squaring ay by is going to be less than or equal to integral square of the first function. So that's going to be d log f x comma theta given y d theta squared multiplied by the square of that. So that's going to be f of x comma theta y dy multiplied by square of the second function, which is f of x comma theta f of either way, f of, let's write it as I had x and y are random variables, theta is a parameter, dy. So what is the value of this? Anybody? So this is f of x comma theta, because we are just integrating out y, like here, right? F of x comma y comma theta is fx theta. So look at the left side. I'm going to write it. So left side is f of x comma theta squared. Then you have d log f of x comma theta with respect to d theta, right? So you get the last expression. Look here, the 1 fx theta cancels on both the sides. So I'll write one more expression, then I'll go there. So what we get is from here, f of x comma, so what we get is a d log f of x comma theta multiplied by, or derivative with respect to this, multiplied by f of x comma theta is less than integral d log f of x comma theta given y, I'm just copying from here, d theta, the whole squared, multiplied by this, because this cancelled out, right? I took care of this, I just cancelled this, so I get only 1. So multiplied by this function, f of x comma theta y comma y dy. Let me write it somewhere else. Okay. So I'm just going to copy that last line. Look, f of x comma theta comma y, I can also write it like this, right? Okay, so this much is true. So I'm going to remove all this stuff. So all I need is, if you agree to the top line, then I don't need anything else. Now what I'm going to do is, remember this integral is with respect to y, right? Because look here, this integral. So I'm going to, there is one more random variable, x, on both the sides. So I'm going to take the derivative with respect to dx. So this reads now d log f of x comma theta d theta squared multiplied by fx theta is less than or equal to integral with respect to x. So with respect to x, so you get d log f x comma theta given y d theta squared multiplied by f of x given y. So this is with respect to dx, and then the whole thing multiplied by fy y dy. So we can flip this if you want. Now look, so this is what? How do you write this? You can write this as expectation, right? So this is left side is expectation of what? Expectation of this quantity, d log f of x comma theta d theta squared. Here you have double expectation, a conditional expectation. See, this quantity is expected value of d log f of x theta given y d theta squared, right? That's the conditional expectation, conditional with respect to y. Then you have another expectation. Of course, the second expectation is with respect to y. First, right? So this quantity is less than or equal to this. So let me put everything together. Let me flip the whole thing on both the sides. So then the inequality will go this way. So look, the left side is familiar to you. This is your Cramer Rao bound. And so we'll call this to be the modified Cramer Rao bound on this side. Both are for the same parameter, okay. So as I said, I mean, my diagram was wrong, so this is the right one. So you have sigma squared CR here. And everything is the other way. If you want to improve a bound, this should go this way. Because going this way, of course, you can say anything is greater than 0. So going this way is not an improvement. It is actually, so this will be the improving a bound, improved CR. Remember, earlier I drove the, and the whole thing is in video now. All right, so this is your modified Cramer Rao bound. Sigma squared is, so the modified Cramer Rao bound is weak. But if it is so weak and you say that something is greater than 0, it has no meaning, right? Right? How come you didn't stop me earlier when I made a mistake? Any of you? Yeah?
No, but we just calculate the Cramer bound of two parameters, unknown parameters, and the bound of each one actually is higher, I mean larger than with only one unknown parameter.
Not larger, maybe larger.
Yeah.
So what is your question?
So actually,
This is a different problem. I am saying in some cases, the problem is so complicated, you cannot compute the Cramer Rao bound. Let me show you an example, okay?
yeah, but
What is your question?
if the bound is, we say it became larger, actually it's improved.
No. What was it where sigma squared CR is, now you are confusing me. Let me see, 1 over J11, right? In one case.
Yeah. Only one unknown, yeah.
And sigma squared CR, you have to read it properly. And it is true, this is, what it means is the following. Let me say it. So you have, oh, hold on, I'll explain. You know what this is? Here, theta 1 unknown. It's a good question, good point. Let me explain to the class what you're seeing. So there is no paradox here. Okay, what it says is that if theta 1 is unknown and theta 2 is known, whatever you do, your variance of your estimator can only go up to here. In this case, the variance can only go up to here. So there will be a degradation. So when both are unknown, you cannot do any less than this. The bound is higher. That means if your variance of your unbiased estimator, remember, let me put double. These two estimators, whatever it is, you find an estimator here. These two estimators may not be the same. Because look, in the case of sigma squared, estimator is what? If mu is known, this is the best estimator, right? In one case. When mu is unknown, the estimator is now xi minus x bar the whole squared over. What I'm trying to say is that these two estimators are different, right? So this estimator variance, what it shows is that, so even though I show it symbolically as variance of theta 1 hat, there is a chance that this estimator can go up to here, okay? Whereas here, this estimator can never go beyond this. So this estimator is going to be worse than this estimator. That's what the bound means, right? No, don't shake your head on after asking. Did you understand what I'm saying? Or did anybody understand what I'm trying to say or no? See, his question was, I guess, looking at this diagram. If a bound moves in this direction, it is an improvement, right? Look at what I'm trying to say. Whereas, see, this moved in this direction. That's not an improvement. What it says is in this problem, you cannot, remember, you want to drive the variance as low as possible, right? This is the bound on the variance. So here the bound is low. Whereas if you bring in more unknowns, that bound naturally goes up, which means whatever you do, this variance can come only up to this level. Remember, this is apple, this is oranges, two different problems. I hope I see the source of confusion, so I hope everybody understands this. Bound is here in one case, right? We also showed that when there are more unknowns, the bound could, let's say bound increases, okay? What does that mean? Whatever is the best variance can only come up to here, right? That's what we mean by a bound. This variance is going to be greater than or equal to this number. Here, this variance is going to be greater than or equal to this number. So there is a possibility this could be as low as this, whereas this is only going to come up to here. So which is of course, that means that in this situation, you may be able to drive the variance up to here, whereas in this situation, the variance will be higher here. So which means that this variance is never going to, or this situation can never be improved upon that the earlier situation. Yes? It seems to be crystal clear to everybody else. I don't think you are not convinced?
Yeah, actually I understand the two bounds separately, and
because I think your problem is you are listening to yourself, not to me. I agree with you, the bound has moved up, right? But that is not an improvement because these are two different problems. A bound moves up, it also means that the variance can, look at it this way. If the bound moves up, the variance cannot go down, right? Go below this. If the bound is here, the variance can come up to here. Yeah. So of course, if you are clever enough, or if the problem allows you, this variance can come to this level, whereas in this case, however clever you are, the variance can only come up to here. So even when both are efficient, if both are efficient, this will be still a numerical value worse than this. So this is a worst case, right? All right, so here, I mean, of course, improvement only comes, look, your actual variance is here, and then you say Cramer Rao bound is here. Then, of course, you can ask, am I here because your bound is sloppy, or is it because I cannot get it? If bound is sloppy, I should be able to improve the bound. That's what. So we are not even going in this direction. That will be Bhattacharaya bound and so on. I'm not going to do it. It will take additional. So sometimes if it is hard to compute, we'll go for a sloppier bound. The sloppiest bound is this. Simply say that the variance is greater than 0, right? That of course is a trivial bound. So let me illustrate. So I give you, you should search the literature. There are many ways to do modified Cramer Rao bound, the Ziv-Sakai bound and so on. This is just one that I happen to like, or I know the derivation for. So this is a weaker bound, weaker, right, compared to this. This is the weakest bound. But if anything, if it is better than this, then this bound is better than this. So I just show, so if you call, this is double expectation. You know what this means. This is expectation is with respect to x. This is with respect to y. Here there is only with respect to x. So let me do a problem that itself should be sufficient. Any questions? What do you think? Have we posted the lectures? The last video is there already, right?
Yeah. I think they're all there.
You were saying no?
I didn't see last week's.
You posted this morning, I think.
Oh.
This morning or last night.
I think I checked 9 o'clock this morning and it was not there.
I'll check the. I'll have to ask a few people. I mean, I'm not in charge of who's
Yeah.
putting that out.
So maybe you can ask John to send us a mail. But you are saying you saw it?
I saw it around 11, 11:30. They uploaded it in 2 different parts.
The office isn't open until 9, so
Yes, it was around 11, so I think you uploaded it in 2 different parts.
they're huge files. I mean, it takes forever to upload.
Remember, generally we are used to this problem, right? An unknown parameter plus noise, right? So here the Cramer Rao bound is easy because this is Gauss, the whole thing is Gaussian with the mean and variance sigma squared. So we just went through this, right? What is the Cramer Rao bound? Anybody? Hello? A Gaussian data, this is mean plus noise. Noise is 0, mean Gaussian. Huh? Yeah, sigma w squared over the number of observations. Let me use number of observations m in order not to confuse with all this. So let's do, this is multiplicative noise, right? The parameter, look at this problem. Parameter gets multiplied by a random variable, and then you add. So you can even stop here if you want, but let's try to do this, okay? Look here, this is unknown. This is Gaussian. So what is x? Anybody, what is the distribution of Gaussian? X, n and w are independent. So at least it is Gaussian with
0. And sigma theta squared, sigma squared plus sigma w squared.
All right, so let's try to find Cramer Rao bound. You have to find the unbiased estimator, etc., which I am going to leave it to you. So of course you can set up the joint density function, right? Is the product of all the observations. So I equal to 1 through m observation. I'm using m because I don't want to confuse with this n. So 1 over square root of 2 pi sigma squared. But you see, you can begin to see now how difficult this is going to be. All right, so you have to do d log f, right? I mean, log f of x comma. First of all, that's going to be, all right, so I already included this, so this is to the power n. So minus n by 2 log 2 pi plus log theta squared sigma n squared plus sigma w squared, right? Minus sigma xi squared over 2, right, theta squared. All right, so there is some work to do. So let's try to, I'll come back to this, but let's see how easy the modified Cramer Rao bound is. Hello, here. So we are going to freeze one random variable. That's the idea on the modified Cramer Rao. Remember, n is playing the role of y before. So if you freeze n, given n, what is the distribution of, n is a constant, so what is the distribution of x? Gaussian with? All right, mean is n theta, and the variance? All right, very good. So let's look at the joint density function of x n is 1 over square root of 2 pi sigma w squared to the power n by 2 e raised to minus xi minus mean the whole squared over 2 sigma w squared. Right? So let's take the logarithm of f of x theta given n is n by 2 log 2 pi sigma w squared minus sigma xi minus so if I take the derivative of this with respect to theta, what do you get? 2 this there is no derivative, right? 2 goes away, so I get summation I equal to 1 through m, right? Xi minus n theta multiplied by?
Divided by 2.
2 gone, right?
Oh, yes.
Multiplied by what?
By n.
By n, right. Now, you know that the squaring is the same as taking the second derivative, right? So squaring is, so let me do the, because we also know that, hello, you know that this is the same as take the second derivative and take the minus with a minus sign, right? So that will be easier. So the second derivative is, remember this is all given n. So that's going to be, remember the summation comes inside, the first term is independent of theta, right? First term has no theta. The second term has theta here. So there are m such terms. So first of all it is minus m n squared over sigma w squared, right? I'm taking the derivative with respect to theta. Now I should take the expected value. So let me just do it here. Expected value of this quantity is expected value of here, n squared. What is the expected value of n squared? What?
N square.
N is a random variable, Gaussian random variable with mean 0 sigma n squared, somewhere here.
Oh, for now, this one is given.
Hmm?
For now, it's given.
Right, but look at here. I'm trying to compute this. So, all right. So it's first expected value with respect to n is going to be itself, right? So he is right. So what he is saying is, if you do the first expectation is with this n, e is with respect to n, but since given n is there, this is this. So I'm going to do a double second time I'm going to do expectation with respect to n. Look here, expectation with respect to x, then expectation with respect to n. I mean expectation with respect to n, now we have to do with respect to the other. So this will be now expected value again, right? Look, here I need one more expected value. This time this will be with respect to n. This was with respect to actually the other one, x, which is independent of x. So this will turn out to be expected value of m n squared over sigma w squared. Look here, one expectation is with respect to x, other expectation is with respect to y. If you try to do this expectation with respect to x, there is nothing. So only thing, you just need to do the second expectation, which is expected to n. With respect to expected value of n, what is it? Expected value of n squared is?
Square, sigma n square.
There is a minus sign. So minus m sigma n squared over sigma w squared. So the modified Cramer Rao bound is what? You just flip it. So sigma squared modified Cramer Rao for theta is minus 1 over this double expectation, right? D squared log over d theta squared sigma w squared over m sigma n squared. Okay, so this was reasonably easy, right? Oh, let's try to complete this, then I think we can. So this is a mess because now you need to take the derivative with respect to so what's the derivative of this log of d log f x comma theta with respect to theta? Look here, you have two terms. This term goes away. So minus n by 2, then theta squared sigma n squared plus sigma w squared, right? Then the derivative of this, that's going to be with respect to theta. So what is it? Sigma n squared 2 theta, isn't it? Where are you looking? Here. Take the derivative of this. So derivative log of something is 1 over that, right? This is right or wrong? Then I have to do the derivative of this. So minus sigma xi squared I equal to 1 through n. Derivative of this with respect to theta. So you have 2, this is theta squared plus sigma n squared plus sigma w squared minus, this becomes plus, then what? Multiplied by the derivative of 1 over something is minus 1 over squared. Then I have to take the derivative of this with respect to theta.
2 sigma n square.
Right, sigma n squared 2 theta, right? Right? What did you say? Jesus, why? 4 theta? Rather than take this second derivative, I'll square this, because try to take the derivative of this. We can do this second derivative, but it will be a messer. It may be messy. So we just do what it says. We just have to square this, right, to find the Cramer Rao bound. Right? There is a bracket here. Yeah.
I think there's this one, because it's summation of sigma I squared away the function itself over 2 sigma squared, right? So the bottom there should be.
Yeah, you are right. Is this what you are saying? Right. All of us got excited. There is a sigma. No. Hold on. If xi is mean with 0 sigma squared, what does that mean? Density function is xi is e raised to minus whatever is this quantity, xi squared over 2 sigma squared, right? So this is the variance. What is the variance of this random variable? It's this quantity, right? So I think I'm good. What he was saying is maybe there is a 2 here, I don't think so. But what he was saying is there is a 2 here. Yes or no?
No.
All right, very good. At least that, no. So this is good. Now you see, I'm going to square this. Remember, I need to square this. So that means I need to square this quantity. And then we'll take the expected value, okay? So help me. So n squared, theta squared, sigma n4 over theta squared, sigma n squared, plus sigma w squared squared, right? Oh, that one term, then the middle term is minus 2n sigma xi squared, sigma n4 over theta squared, sigma n squared plus sigma w squared. You can see, and this multiplied by this, so that's cubed, right? You can see the Cramer Rao bound is messy, whereas the modified is a bit easier, right? Then you have to square this, okay. So that's plus sigma xi squared, the whole squared, theta squared sigma n4 over theta squared sigma n squared plus sigma w squared, the whole thing to the power 4. If I did not make any mistake, now we need to take the expected value of this quantity here. So let me do an expected value. So that
with respect to W and N simultaneously.
what?
Now we need to.
There is only one random variable here, right? Look at here, the way it is done. The random variable is x. You saw the density function here. This is all constant. There is no W here now. Randomness is with respect to x. What was the problem? Remember, we concluded that, right? X is 0 mean with the variance theta squared, sigma n squared plus sigma w squared. So when you write the density function, there is no, everything is with respect to observations. Whereas in the modified Cramer Rao bound, we did a shortcut. We froze n, did this, and then found the expectation. Yes, this expectation is with respect to what you see, which is x. There is only x here. So expectation of this is a constant. So you need expectation here. You need expectation here. We'll come to that in a second. All right, so that's easy because n squared, theta squared, sigma n4 over theta squared, sigma n squared plus w squared, the whole squared. Here you see what is the expected value of this, I equal to 1 through m. Each of them is 0 mean. So expected value of xi squared is, each xi is like this, right? Each xi is like this. So expected value of xi squared is this quantity. There are m such, then I'm just totally, this is your m, number of observations, right? Is that what was, you got confused? You were asked. So this is m squared. This is number of observations. I equal to 1 through m. Okay. All right, look at here. If I did right, this is m multiplied by theta squared sigma n squared plus sigma w squared. One cancels, so I get minus 2m squared, same as this, right? So this just becomes minus, right? Because minus 2m squared sigma n4, there was also a theta squared. What happened? Oh. And none of you are paying any attention. The middle term, what is it? So the squaring, you get this. This multiplied by this, there is also a theta squared, isn't it? This multiplied by this. Sigma n squared gives you sigma 4. Theta gives you theta squared. This is the same as m. So m is here. So this is m squared. So this term is identical to this because this is 2, this is 3, but this will cancel with this, giving us 2. So you get that. Now, just the last term. Remember, sigma. Now we need to do this. This is also a bit of a mess because each xi squared is. So squaring, you can write this as double summation xi squared sigma xi squared. How do you do that? All right, so it goes like this. Sigma xi over square root of theta squared sigma n squared plus sigma w squared is chi squared, okay? This is chi squared. This is I equal to 1 through n is chi squared with n degrees of freedom. So if I call this to be y, y is chi squared with n degrees of freedom. So its variance is 2n. So this is the same as saying that theta squared sigma n squared plus sigma w squared. This is why modified Cramer Rao bound is much easier. If I pull this out, you get this identity, right? So the variance on the left side means what? The square of this, theta squared sigma n squared. Right, so plus w n squared multiplied by the variance of y equals the variance of this quantity. This is what we want. We want this quantity. They are all so variance of this quantity, remember from here, variance of this is the same as variance of this. Variance of this is a constant multiplied by y. So the constant squared multiplied by the variance of this. But from here, variance of y is 2 multiplied by m because y is chi squared. So now you can, this quantity is, the answer is here, 2m multiplied by this. So you plug it in here. So this whole quantity, if I am not mistaken, it is 2m multiplied by theta squared sigma n squared plus sigma w squared, the whole square. So this whole squared. This cancels with this, you get power 2. So the answer turns out to be 2m I had a different answer in my office, I thought. Anyway, go home and check this out. Of course, the whole thing should turn out to be positive, right? There is a sign issue. I don't know. Let me see what answer I have. Is this right? Is this minus and plus, or no one knows at this point?
That may be a double solution.
Why? Look, I'm saying, let's say, look at this problem. That's not double summation. Suppose xi's are, suppose xi is Gaussian with the 0 means sigma squared. Okay. So how do you compute this quantity? I want the variance of this quantity. So let me call this quantity to be y. So this is true, right? Y equal to, I'm defining y to be this, okay? Right? I'm just defining y to be this quantity. Anyway, it looks like I missed a sign somewhere, so go back and check it out, because of course the whole thing should turn out to be positive. But it's impressive. Already you can see sources of error. So if you don't want to do this or it's intractable, then you do the modified Cramer Rao bound. Okay. So complete this up. Let me see whether I have the exact answer. So maybe somebody can put this up and see where the sign went wrong. One sign seems to have gone wrong. And I have the answer as yeah, I have, for whatever reason, I don't have the minus seems to have gone away. I don't know why. Oh, let me answer this, then we'll double check. I think there is no minus here, okay? And I'll show you why. Let me explain to you why. So the question is, how do you find this quantity, okay? Right? And you know that this is chi-squared with m degrees of freedom, right? Yes? Why? Because xi's are 0 mean. So y over sigma squared is sigma xi over sigma the whole squared. This is normal with, inside is normal with the variance one. That's what we, so this is chi-squared with the m degrees of freedom, right? This one. All right, so you see, so you know that variance of y over sigma squared is 2n, right? Because this quantity is chi-squared with, chi-squared has the property, if I remember right, mean is m, variance is 2m. So of course variance of y is sigma 4 2m. Because the constant will come as square, right? Right? That's what I used here. Now let me, before we quit, let me just see whether the f was right or not. Why that minus sign? So one more time, f of x comma theta is square root of 2 pi theta squared sigma n squared plus sigma w squared to the power n to the power m e raised to minus xi minus there is nothing minus, right? Remember, xi was normal with 0 mean, variance was, so I'm just writing that expression. So the whole thing to the power m e raised to minus okay, so let's quickly look at the log f and see where I went wrong. So log f of x comma theta is m by 2 log, yeah, see there is, whatever I write, you are not going to challenge. There is a minus, right? Because it's the denominator minus m by 2 log theta squared sigma n squared plus sigma w squared minus sigma xi squared over so let's take the first derivative. This is where we went wrong, I think. So what is it? No, it seems to be right. So you have log of something is theta squared sigma n squared plus sigma w squared minus m by 2. Then you have the derivative of this 2 theta sigma n squared. So the minus is there, right? Anyway, you have to check it out where it, okay, so, and then the derivative of this is minus sigma xi squared I equal to 1 through m. Theta squared plus sigma n squared plus sigma w squared. So the derivative of this is 1 over x is minus 1 over, right? What is the derivative of this quantity with respect to?
Yeah, you should have a minus.
Plus, right?
Times 2 theta sigma.
And I think there was a 2 here before, right? There's a 2 here.
Sigma n squared.
Sigma n squared, right? Right, anyway, check it out. Maybe somewhere there is a correction you need to make. So anyway, when everything is said and done, you flip this will give you the Cramer Rao bound, okay? I will also do it at home and see what the answer turns out to be. So this is end of estimation, right? And maybe just a few, anybody wants to ask anything immediate? So anyway, this 2 goes away. Let me see quickly where I can find the mistake. So point is there is a minus m here, right? Right? Log m by 2. So if you square this, as we said, we have the square of that, m squared theta and the 2 goes away, right? this multiplied by this, that is 3. Expected value of xi squared is same thing as the denominator. So again, you will get this. So that seems to be right. Now it's possible maybe the last term is not done right. I mean, if this turns out to be m squared, everything is fine. But let me see whether we missed an m somewhere. Yeah, I think everything is good. You see, where was the last term? Oh, okay. So there is no m. Is it? This quantity is what? We want the variance of this. Maybe I didn't do this right, is it? Or I did? So the question is, what is this? This is not the variance, I'm sorry. This is not the variance because, so, xi, so xi over sigma squared is chi squared with 1 degree of freedom, or summation I equal to 1 through n. This if I call y, expected value of y is n, expected variance of y is 2n. So expected value of y squared is what? 3n, right? Yeah, 2n plus n squared, right? That's where I made the mistake, right? So look here. This is, so let me pull out that sigma outside. So I get sigma 4. I mean sigma squared multiplied by y is the same as xi squared, right? This much is correct, right? So now I want the expected square of this. This is an identity. I just pull it outside. This is true. Now from there I know sigma 4 multiplied by expected value of y squared equals summation xi I equal to 1 through m squared, the whole squared. Look here. This is what I want. I want the expected value of this. So expected value of this is the same as expected value of this multiplied by this. We just concluded this is 2m plus m squared multiplied by sigma 4. So I just went wrong here. So this quantity I'm going to replace it by 2m plus m squared multiplied by sigma 4. Sigma 4 is sigma theta squared, sigma n squared plus sigma w squared, the whole squared. So this cancels with this, 2 squared is here. Now look at here, m squared, there was a minus sign. So this term cancels with this m squared. Here, this is here. So this answer here, this is where I went wrong. So the answer here is 2m. This was plus, this is minus 2m plus m squared multiplied by theta squared sigma 4. So if you copied all this, it's too late now. So you get 2m theta squared sigma 4 sigma w4, right? This is sigma w, sigma n or sigma n squared, sigma n4 over theta squared sigma n squared plus sigma w squared. So this problem by itself, you should redo this at home. So this is the expected value. So the Cramer Rao bound here, Cramer Rao bound turns out to be 1 over that quantity. So this will turn out to be theta squared sigma n squared plus sigma w squared So you see, as m increases, again the variance goes to 0 as it should. But the point is much more complicated than the other bound. The other bound is, where was it? The other bound turned out to be minus of this. So the modified versus the modified Cramer Rao bound is simply sigma w squared over m sigma n squared. Also goes to 0. All right, right. Yeah. All right, so this is square. So that, of course, I made so many mistakes, right? So more complicated. But that's a better bound. Now, do you clearly see that that's worse than this? I mean, this is worse than that. In other words, this quantity should be here, and this should be here. This is a better bound, but harder to compute. Is it this way or right? I guess you can probably see, right? If you pull out sigma w squared, you still can. And moreover, the actual bound depends on theta squared and so on, right? Yes? Lot of calculations. So hopefully if you do some of this will turn out to be good. So this is a multiplicative noise case, right? The last case we have done. Remember, I used this identity. Variance of any random variable is what? Expected value of x squared minus expected value of x the whole square, right? So the square of a random variable is variance of a random variable plus mean squared, right? So if x is chi-squared, its variance is 2n, mean squared is n squared. Fine?
You get direct calculus.
You may be right. I'm tired, right? Absolutely right. Yeah, he is saying that you can also expand it and do it, right? I agree with you, right? But nothing wrong, right? I don't want to go out without giving you the right answer. So again, you can so if you have too many, the idea of the modified is if you have too many uncertainty, too many random parameters, you can obviously you can freeze this, right? You can generalize this. Suppose x is a function of theta and n and w and something else n1. All these are noise. You can start freezing them one at a time and find the bound. So you can do modified and modified again. You can have a triple expectation. X bound will become weaker. So you may be able to find another weaker bound. This is sigma squared, modified Cramer Rao bound. If you keep modifying, you will reach 0.